Okay, this is section 3.3, how derivatives affect the shape of a graph. What I would say in particular is that this lesson is probably, I don't ever like to say one of the most important, but it really is one of the most important lessons. The better you understand all the concept behind this lesson, the more all of this stuff is really going to make sense. So this is one that you're probably going to want to really focus on. Make sure you really get the concept. And if you have to, rewatch some of this stuff just to make sure. None of what we're going to be doing is extremely difficult. Sometimes algebraically, sometimes some of this stuff can be difficult, but conceptually it's not really that difficult, but you really do need to understand it. This is going to really start taking a lot of the things that we've learned and kind of putting them all together. All right, so let's take a look at this. We're going to explore the relationship between the derivative and graphing functions, so how it fits together. Okay, one thing I want you to keep in mind, derivative is a slope. Okay, so when we see derivative, we should be thinking slope. Specifically, it is an instantaneous rate of change. So an instantaneous rate of change. Okay, it's a tangent slope. It's not the secant, not an average. It's the instantaneous rate of change, but it is a slope. Okay, let's talk about what's called the increasing/decreasing test. If f prime, which is your derivative of x, is greater than 0 on an interval, then f is increasing on that interval. Let's stop right there before we even go to the second sentence. If f prime, which is your slope, is greater than 0, that means your slopes are going to be like 2 or 7 or 15 or whatever they are, but they're positive values. If a slope is positive, think about it graphically. Slope's positive, that means the function is going up. It is increasing. A slope everywhere on that thing right there would be positive. The tangent line slope here is positive. Positive slope, positive slope, positive slope. The function is increasing. Likewise, if f prime of x is less than 0, then f is decreasing on the interval, meaning if the slopes are negative, then the function is coming down. Okay, so positive slope means the function is going up. Negative slope means the function is coming down. All right, let's do a really quick, well, should be a relatively quick example. What we have is a polynomial function that you see here, f of x. We simply want to figure out where is this function increasing and where is it decreasing. So the fact that we're asking where means we want intervals. We want intervals of x values. So if we were to graph it, you would say, okay, from x equals this to x equals this, the function is increasing. From x equals this to x equals this, the function is decreasing. So you're going to use interval notation. We're also going to introduce our sign analysis on this one. And use a number line to kind of help us. I want to stress something when we get to that. But ultimately, if we want to figure out where something is increasing or decreasing, we want to know where the slopes are positive and negative. That's what we just talked about with the increasing/decreasing test. So if we want to know where the slopes are positive and negative, we need a derivative because derivative tells us slope. So f prime is going to be 12x cubed minus 12x squared minus 24x and plus 0. Okay, so here's the thing. If I want to figure out where this thing is increasing or decreasing, I could obviously just start picking random values of x and hope that I can figure it out. That's going to be difficult. What I really want to know first is I want to know the critical values. I want to know where the slope is 0, because if I know where it's 0, which is where it's neither increasing nor decreasing, then I can figure out everywhere else that it is either increasing or decreasing. So we want to take that derivative and set it equal to 0 to find critical values. Let's do a little bit of algebra here. We can factor out 12x, it looks like. which is going to leave x squared minus x minus 2. So we're going to get 12x, the x squared minus x minus 2 factors. Looks like that's going to be x minus 2x plus 1. So the x values where the slope is 0 is going to be x equals 0 from the outside factor, x equals 2 from the middle factor, and x equals negative 1. So what we're going to do is we're going to create ourselves a number line. And on this number line, we're going to put our critical values. All right, make sure we put them in the correct order from left to right. So it looks like we've got negative 1, 0, and 2. And what we're going to do now is we're going to check values around the critical values. So at the critical values, the slope is 0. Because if I were to plug negative 1, 0, or 2 back into the derivative, it's going to give me 0. So it's not increasing or decreasing at those values. In order for a function to go from up to down, it has to hit a critical value. When it hits the critical value, it's going to have a slope of 0 and then change. Now, we could have critical values where it's undefined as well. We'll talk about those when we get to them. In order for a function to go from down to up, it's going to hit a critical value. So the idea is, since I only have 3 critical values, whatever this function, let's just say in between 0 and 2 is doing, it will always be doing that. It's either always increasing or always decreasing. It can't change direction because in order to change direction, it would have to have another critical value. And there is no more between 0 and 2. So whatever value I elect to try and pick between 0 and 2, whatever that is, if I figure out if it's increasing or decreasing, everything between 0 and 2 is doing the same thing. So the concept is, let's go ahead and take a number in between and around all of these values. So let's take something which is left of negative 1. Pick easy values to work with. The easiest value probably is negative 2. So this is what I mean about sign analysis. I could plug negative 2 back into the original. It's going to take a little bit of work, but we could obviously figure it out. There's a much easier way. What if we plug negative 2 back into the factored form? And here's the thing. I don't necessarily need to know the value. As a matter of fact, it's probably a waste of time in this case. All I need to know is what the sign is going to be. That's why we call it sign analysis. I'm going to analyze the signs of this thing. So if I were to plug negative 2 into 12x squared, 12 times negative 2 is a negative number. I don't care what it is. I mean, I know it's negative 24, but I don't really care. If I plug negative 2 in here, negative 2 minus 2 is a negative number. So far I have a negative and a negative. And if I plug negative 2 into here, negative 2 plus 1 is also a negative number. So what I have are 3 negatives being multiplied together, which means that it's going to be negative there. And since the derivative is negative, that means the function is decreasing, coming down. That's what a negative slope means. It means the function is decreasing. Okay, we're going to do exactly the same thing. Now we're going to do something in between negative 1 and 0. And this is really why the sign analysis is important, because now we're dealing with fractions. Something in between negative 1 and 0 is going to be a negative fraction. Again, just take something easy, negative 1/2, negative 0.5, plug it into all 3 things. So if I plug it into 12x, I'm going to get a negative. If I plug it into the x minus 2, negative 1/2 minus 2, still negative. So I got 2 negatives. If I plug it into the third one, however, negative 1/2 plus 1 is a positive value. So I got 2 negatives times a positive. 2 negatives make a positive when you multiply them, times another positive is still positive. So the function is increasing. If I take something in between 0 and 2, like 1, plug it into 12x, that's positive. Plug it into x minus 2, that's negative. Plug it into x plus 1, that's positive. So I get 2 positives times a negative, which makes a negative, meaning decreasing. And then if I take a number greater than 2, like 3, plug it into 12x, x minus 2, x plus 1, all of those are positive. So multiplying a whole bunch of positives together gives you a positive, which means increasing. Now, the reason I put those little arrows on there is because it kind of gives you the general shape of the graph. So if you really look at it, while this is not a perfect sketch, it just shows me that the graph does something like this. Okay, my shape may not be perfect, but it's the general shape of it. Now, ultimately, what I was looking for was, where is the function increasing, where is it decreasing? Well, again, the arrows kind of tell us that as well. So the function itself is going to be increasing. The first interval where it's increasing is in between -1 and 0, because that's where the arrow is going up. So from -1 to 0. The second interval where the function is increasing is going to be from 2 off to infinity, it looks like, because it never changes after that. So in union with 2 to infinity. All right, and where is the function decreasing? Well, it's going to be, in this case, the other intervals, which is going to be from, let's see, it's decreasing from -infinity up until it gets to -1. So -infinity to -1. And then it's also decreasing from 0 to 2. Now, notice on mine, I put parentheses around everything. There are times where maybe you're going to have a solid bracket if the number is included. In our case, infinities can never be included. And at -1, 0, and 2, the function was neither increasing nor decreasing. So I choose not to use the solid bracket. You will actually see sometimes where maybe problems use those, and there's actually some debate, I guess you would say, among people who would say, oh, it's actually included. No, it's not included. I personally don't include it because, as far as I'm concerned, if you have a slope of 0, the function is neither increasing nor decreasing. So I don't include them. And that's the way I pretty much feel like we should be doing this one. Okay, let's look at the next thing. So that's the increasing and decreasing. The first derivative is going to tell you increasing and decreasing. It's going to tell us some more information as well. So the first derivative test says, suppose that C is a critical value, or a critical number of of a continuous function f. So it does have to be continuous. So suppose that C is going to give us a critical number of a continuous function. If f prime, which is your slope, which tells you direction, changes from positive to negative at C. Okay, let's take a look at what that would look like. So I have a function which is going to change from positive slopes to negative slopes. This must be your C value right here. If we were to kind of draw like a line right there. Changes from positive slopes to negative slopes. Then what are you going to have at the top here? Well, that would be a local maximum. So if the derivative changes from positive to negative at a specific C value, then you're going to have a local maximum. Likewise, if f changes from negative to positive at C, I'm sure you probably already guessed it, from negative to positive at C, then you're going to have a local minimum. Oops. So again, you just have to remember that the derivative is the slope. It tells you the direction that the function is going. So if something goes from up to down, then you're going to have a maximum at the top. If it goes from down to up, then you're going to have a minimum at the bottom. And then we have the case where maybe f prime doesn't change sign at C, and that can happen. If that's the case, so like an example would be if f prime goes from positive to positive on both sides of C, or from negative to negative, then f has no local max or min. And let me show you a couple cases. There's 4 of them actually where you could see stuff like this. So we'll go with, excuse me, I've already kind of sketched it for you, but we'll go with A first. A was the case where we had a positive slope to a negative slope, positive slope to a negative slope. So at some value C, right here, you're going to have a local maximum at the top. Okay. Letter B was where we had a negative slope to a positive slope, negative slope to a positive slope. And then at this value right here, C, you would have a local minimum because it went from down to up. Now, let's go ahead and take a look at the other examples where maybe you have a critical value, because maybe the derivative is 0, but it doesn't actually change sign. So we could have one where the slopes are positive. We hit an instantaneous slope of 0 right there, and then they are still positive afterwards. So we'll put our C value right there where it looks like maybe it levels out for 1 second. But you can see how you would have positive slopes to the left of C, but still positive slopes to the right of C. There would be no local max and min there, because obviously it's not going to be higher or lower than anything right there. And then you could also have the case where it goes the other direction, where it's going to come down. So it's negative, 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 0 for a second, and then still negative. So we'll put our C value like right there. Mine flattened out a little bit too much. It was supposed to be more curved, except for at that 1 point C, but that was just my drawing. Hopefully you understand the concept there. Okay, so we can tell where we have local maximums and local minimums based upon what the slopes are doing. We've already figured out increasing and decreasing. Well, we can just take that same information and figure out, do we have local max or local min values? As a matter of fact, let's go ahead and look back at the previous page just for a second. Just from the sketch that we did from our number line, we should be able to tell that right here would have been a local minimum because it went from down to up. Here would have been a maximum because it went from up to down, and right there would have been a minimum because it went from down to up. So again, we kind of already did the work. There's only a little bit extra that we're going to have to do. All right, let's move on to page 3. And we're going to do this example specifically using f of x equals x plus 2 sine of x. We want to find the local max and local minimum values of the function. So let's go ahead and do that. In order to do that, we need to find the critical values first. Very much like absolute maxes and mins, we have to find critical values. The only difference is we're not testing the endpoints, because remember, you cannot have locals at the endpoints, which we did talk about in, I believe it was 3.1. Could be wrong, could be 3.2. I'm pretty sure it was 3.1. All right, so let's go ahead and take our derivative. So f prime, see, derivative of x is 1, derivative of 2 sine of x is 2 cosine of x. We want to find the critical values, so we'll set that equal to 0. Solving that for cosine of x first, we'll subtract 1 on both sides and then divide by 2, so we get the cosine of x is negative 1/2. So now it's only limited to between 0 and 2 pi, which is good. So I just need to figure out what values on the unit circle this occurs. Let's see, cosine is going to be 1/2 at all of the thirds, the pi thirds. So we just got to figure out cosine is negative in second and third quadrant, which is going to make that 2 pi thirds and 4 pi thirds. So those are our critical values. We're going to set up a number line, just like we did before. All right, and this is kind of important. Obviously, we're going to write these things in the correct order. But we also have a closed interval here. So I'm actually going to put over here my closed endpoints of 0 and 2 pi, so I can't use test values outside of those. But notice I put a solid bracket on those, and the reason I did that was because 0 and 2 pi are not critical values. Okay, we did not get the slope to be 0 there, so we can use those values as test points. And that's important because when we're dealing with sine and cosine, and even for that matter, a lot of the other trig functions, 0 pi and 2 pi are probably the easiest values to pick. There are several others that we could pick based upon unit circle stuff, but those are probably the easiest ones. So let's go ahead and figure out positive and negative slopes, because once we do that, we're going to be able to see where we have local max and mins. So if I want to take something which is less than 2/3, for example, let's use 0. We will plug 0 into our derivative. So the f prime at 0, let's see, it's going to be 1 plus 2 cosine of 0. Cosine of 0 is 1. So 1 plus 2 is a positive number. Yes, it's 3. It's not really something I needed to know. It is positive, which means the function is increasing. Something in between 2 pi thirds and 4 pi thirds. Well, something in between second and third quadrant, the easiest value to pick is pi. Again, if I plug that into my derivative, f prime of pi. So cosine of pi is negative 1 times 2 is negative 2 plus 1 is a negative value. So that would be decreasing in between there. And then the last interval I can pick, something greater than 4 pi thirds. Well, again, I can use 2 pi because it's part of my interval and it's not a critical value. So if I plug 2 pi in, it's going to give me exactly the same thing that it did at 0, since cosine of 0 and 2 pi give exactly the same values. So we know that this one is also positive, which means increasing. Now, it didn't ask for increasing and decreasing, but we found it anyway because it's the easiest way to figure out, okay, the function went from up to down at 2 pi thirds, which means that's the location of a local maximum. So our local maximum, just like absolutes, they want the y value. So it's good to know the x value because we need to know that to get the y value. So we're going to say that the local maximum is f of 2 pi thirds, which is going to be if I plug 2 pi thirds back into the original function to get the y value. So that'll be 2 pi thirds, plugging it in for x, plus 2 sine of 2 pi thirds. Sine of 2 pi thirds is going to be positive 1/2. Positive 1/2 times 2 is I'm sorry, it's not positive 1/2. It's positive square root of 3 over 2. Times 2 is just going to give us a square root of 3. Okay, hopefully that's something that you guys can see mentally without me having to write it down. If you need to write it down just to see it, please do so. And then our local minimum value we know is going to occur right here because the function went from down to up at 4 pi thirds. So the local minimum will actually be f of 4 pi thirds, which is going to be plugging 4 pi thirds into x, 4 pi thirds plus, now sine of 4 pi thirds, that's third quadrant, so that'll be negative. So actually I'm going to make that minus. Minus 2 times square root of 3 over 2. Again, the 2 and the 2 are going to cancel out, so you get minus square root of 3. So there's our local maximum and local minimum. All right, we will come back with a second video, and that should finish this up.